Hello, everyone. Welcome to the MIF++ seminar. It's a pleasure to introduce Professor Gil Alon, who will talk about continuous symmetry measures of molecules and crystals. Over to you, Gil, please.
Hi, Vitaly, and thank you very much for inviting me to talk in this seminar. It is a little bit strange because I cannot see you for some technical problems, but so I think it will be another reason for you to feel free to intervene every once in a while so that I will know that you are with me and I'm not just speaking to the wall. And this is a joint work with Professor Inbal Tuvi Arad from the Open University in Israel. I myself am a mathematician, and Inbal is a chemist, and we have been collaborating for 8 or 9 years on this project of symmetry measurement that I think is a very nice blend of mathematics, algorithms, and chemistry. So I will try to be both general for some people who do not have background in either of these fields and specific at some parts of this talk. So let us start with the concept of pseudosymmetry or approximate symmetry. And symmetry, of course, is everywhere and is very important and beautiful. So we can look at this butterfly that has this axis of symmetry. And mathematically speaking, a symmetry is an overlap of an object under an isometry, transformation of space which preserves the distances.
Gil, I think we lost your slides.
Okay. You don't see my...
Oh, yeah, back. Now you're back.
Now you see the butterfly? Okay.
Yes,
okay,
yeah, fine.
So,
yeah,
okay, but now let's see if I can scroll.
Gil?
Yeah.
Yes.
Okay,
Yes.
I will just use my mouse. It's sorry for these technical difficulties. Let me see if I can do it like this. No, now it's not. Okay, let's try it this way. Not the most optimal way, but at least you can see everything. Okay, so now you can see the butterfly?
Yes, we can see. Thank you.
Okay. So as I said, this butterfly, it has a reflection symmetry. So in this case, the isometry will be just a reflection with respect to the symmetry axis. But more often than not, the symmetry is not perfect. If we look, for example, at our bodies, they're nearly symmetric, but not exactly symmetric. So this is what we call an approximate symmetry. And the continuous symmetry measure tries to measure how far an object is from perfect symmetry. So in shorthand, it is called the CSM. So you can ask why bother quantifying symmetry? So from the perspective of chemistry, it is very useful. So one thing is that symmetry has a lot of meaning in chemistry, and sometimes we can detect some exact symmetries, but other symmetries are not exact and they are hidden, and we would like to expose them. So this quantification allows us to decide whether this hidden symmetry is significant enough. And the symmetry has many roles in chemical processes. So many characteristics of matter are in correlation with symmetry. So having a numerical value of the level of symmetry allows us to analyze these processes in a higher resolution. So the outline of this talk is, first, I will explain to you how this symmetry measure is defined. I will discuss in detail our algorithms for calculating this measure. And I will show how we use it in the world of crystals, which is our more recent work. So let us start with molecules, which are smaller objects than crystals. So a molecule in this talk is just a collection of atoms in space, a finite collection, and each atom has a type. So it is one of the elements. It can be hydrogen, oxygen, etc. And each atom has a position in the three-dimensional space. And some atoms are bonded to each other. So in this picture, we have this ball and stick representation. So the balls are the atoms, and the sticks are the bonding relations between them. And in such a case of a finite object, so the asymmetry of the molecule, it must preserve its center of mass. So if we look at all the symmetries of the given molecule, it has a group structure, the symmetry group of the molecule, and all of them preserve the center of mass. So for this reason, it is called the point symmetry group of the molecule, or a point group.
Gil, could I ask, by center of mass, you mean the geometric center without taking into account masses or weights of atoms?
Yes, yes. We are in our analysis, we are not taking them into account, but of course, you could equally take them into account. But in our algorithms, we don't do it. We look at the molecule as a purely geometric object, or we can look at it as a colored graph. So the graph, the nodes of the graph are the atoms, and the colors are the atom type, and the edges are the bonds, and this colored graph is also embedded into space. So thank you for this question. Yes, so the possible symmetries are the identity, rotations, reflections, inversions. So we only have one inversion at the center of mass, or an improper rotation. It is not crucial to discuss the details, but those are all the possible isometries of space which preserve a given point. So now let me describe to you the definition of the continuous symmetry measure. So let's denote by Qi the positions of the atoms of the molecule. And let us suppose that there is a certain type of a point symmetry group. And then we define the CSM by this expression. So the 100 is, of course, just for normalization. And in the numerator, we take the minimum of the sum of square distances between the atom positions and the positions of an ideal structure, pk, where this structure P1 to Pn is perfectly symmetric under the group G. So we basically look at the L2 distance of our molecule from a perfectly symmetric one according to the symmetry group or symmetry group type. And in the denominator, we have this normalization factor, sum of squares of distances between the atom positions, and Q0, which is just the center of mass. So let us consider this definition for a minute. Oh, sorry. And try to understand why it is a measure of the symmetry. So when the molecule is perfectly symmetric, then we can just take qk equal to pk, and then the measure is 0. So 0 stands for for perfectly symmetric structure. On the other hand, this number is always bounded by 100. It cannot exceed 100, because if we set all the atoms pk to be q0, then it is perfectly symmetric. It is invariant under the group, and we obtain exactly 100. And since we are taking the minimum, so it cannot be more than that. So this is the idea. And so, for example, if I look at this blue triangle, Q1, Q2, Q3, then I'm taking the minimum over, supposing that our symmetry group is a threefold rotation. So I'm just looking for equilateral triangles, and I'm looking for the equilateral triangle that minimizes this expression. All right. So as I said, it is always between 0 and 100, and 0 corresponds to the perfect symmetry. So the main question here is, how can we calculate this measure? Because you might say that it is just a formula, but this formula includes a minimum. So this is actually an optimization problem that needs to be solved. And this is where our algorithms come into play. So we will focus on the case where the group G is cyclic. So it is generated by just one type of symmetry, T, of order n. So it can be, of course, any type of the symmetries that we discussed before. So this might seem like a very specific case, but actually it allows us to analyze all the types of symmetries. So it is actually quite powerful. So this isometry is given by some geometric data that we call the symmetry element. So, for example, if it's a rotation, then we need the vector around which the rotation happens. And if it's a reflection, then we need the vector which is perpendicular to the plane of reflection. So we can always describe the isometry by a vector in Euclidean space. And the perfectly symmetric structure is supposed to be invariant under this isometry. So if it's invariant, then it takes any atom in the symmetric structure to another atom. So it permutes the atoms. So it defines a permutation, which we denote by pi of the atom. So if we take pk, then its image will be p of pi k. And the nice thing about it is that it goes also the other way. If we're just given this permutation and the symmetry element, then we can reconstruct the structure pk. It is quite easy to find the nearest structure that is symmetric under this T and with respect to this permutation and is closest to the original molecule. So, so for example, in the previous example, the isometry is just a threefold rotation, so the permutation will take P1 to P2, P2 to P3, and P3 to P1. All right. So now we transformed our mission to finding one permutation and one vector. So one naive algorithm is just to try all the possible permutations. So if it's a small molecule, then this is feasible. And this was actually implemented because for a given permutation, finding the right vector is quite simple, and it can be done in a constant time. But as the permutation gets larger, then the factorial grows very, very fast. So this will only work for very small molecules. So our idea when we started to work on this project was to exploit the extra data. So first we have the data that the atoms, they have types. So the permutation also needs to preserve the type of the atoms. So this really narrows down the number of permutations. And this actually was already implemented in 2008 by Pinsky and collaborators. But still, this was not too efficient. So we still have this number, which is a product of factorials of the size of the atom type groups. So this still works for small molecules. And our idea was to use the extra information of preserving not only the atom types, but also the bonding relations between the atoms. So we started thinking about it in 2017. And let us call a permutation structure preserving if we have the following condition. So for every pair of atoms, I and J, if I and J are bonded, then their images under the permutations are also bonded, and vice versa. So if we think about the graph of bonding relations, this means that the permutation pi is an isomorphism, is an automorphism of the graph. So let us look, for example, at this example of the ethane molecule. So we have here two types of atoms, and because I'm not a chemist, I don't remember which ones, but 1 and 2 are of the same type, and the other ones are of the same type. So if we know that the permutation is structure preserving, then this means that if it takes 1 to 2, then it has to take 3 that is bonded to 1 to something that is bonded to 2. So it can only go to 6, 7, or 8. So this really narrows down the set of possible permutations, because this condition needs to hold for all pairs of atoms. So our algorithm enumerates only the structure preserving and of course the atom type preserving permutation, and also they have to be of the same order as our isometry. So let's see how this is done. So we work by a search tree where the nodes are partially defined permutations. So they are just permutations that are not defined for all the atoms, but for some of the atoms. So initially, they are not defined for any atoms, and we start filling these values. So when we are at a certain node, then we have to choose which atom we want to decide the value. So it's like solving a Sudoku, right? At each stage, you have a certain, you can choose which box you want to fill or which number you want to find out where it goes, and so on. So heuristically, we just take the atom with the least number of possible assignment, and then we branch the tree according to these conditions on the permutations. So this algorithm works surprisingly well. So for example, we have this molecule called the fullerene, which has 60 carbon atoms. So initially you have 60 factorial, which is, of course, a huge number, more I think, than atoms in the universe or something like that. But the algorithm only needs 6,000 branches to find all the structure preserving permutations, and there are only less than 100 of them. So yes, the exhaustive search would take 10 to the 82 steps. And yes, so now I want to describe another family of algorithms, which are the approximate algorithms, because the exact algorithm that I described will only take you so far. It can work for sometimes molecules of several hundreds of atoms, depending on the structure of the molecule. But for very large molecules, at some point, it will still be too large. So we have to use some approximate methods. So this idea was initiated by Chaim Dreizoun and his coworkers in 2011, and they had the following idea. If we have the symmetry element, the vector that determines the isometry, then we can more easily find the best permutation, which minimizes this expression, which is some measure of how well this isometry and permutation work together. And vice versa. If we have a permutation, then we can find the best symmetry element that works for this permutation. And then we just do iterations. We start with some random vector or some educated guess of the vector, and then we go to the permutation, and so on and so forth, until hopefully we converge to the right solution. So this is what is described here. And so again, this algorithm works pretty well, but it has some limitations, and we tried to improve it. So we noticed that the underlying problem of finding the best permutation is to minimize this expression. So if we go back to the previous slide, we want to minimize this expression of the distance between the transformed image of an atom and the image of the permuted atom, so to speak. So we can put all these numbers in a matrix, and then this boils down to the following problem. So we have a matrix of numbers, and we need to choose one element from each row and from each column, like this, such that the sum is minimal. So this choice is defined by a permutation of the number of atoms. So the permutation tells us at each row which column to choose. And this turns out to be a very famous problem. It has many names. It is called, for example, the secretary problem and the assignment problem also. And there is a very efficient algorithm called the Hungarian algorithm, which was invented by Kuhn in 1951, which does it in, sorry about this, which does it in polynomial time. So this way we were able to optimize the accuracy of the algorithm that initially it just used a greedy algorithm, just take one atom and then find the best value and then go to the next atom and so on. So let me summarize the improvements that we had. So this use of the Hungarian algorithm was the first one. The second one is sometimes we have molecules that are in fragments. So we have this in some types in protein. So like here, for example, we have 5 separate molecules that behave like that are organized in this structure. And then we do the Hungarian algorithms on a 2-level way. So first we find the permutation, the big permutation between the fragments, and given this permutation, we look for the best permutation from each fragment to the assigned fragment. And yes, and for proteins, we also have the chain sequence information. So for example, for DNA, so we can use this extra information from the protein to not only divide the atom by the type, but also by their role in the chain. So this really narrows down the possible permutations. Yes, and finally, or almost finally, we do not just take one guess for the initial vector, but we actually want to try all the possible directions. So of course, it doesn't matter to us if we take the vector or some multiple of the vectors. So we actually look for some point on the unit sphere. So for this, we used an approximation called the Fibonacci lattice, because there is no way, general way, to distribute n points on the unit sphere exactly in a uniform manner, but there is a very good approximation called the Fibonacci lattice. So here it is displayed for some value of the number of directions that we want to try. And finally, we have a combination of the exact algorithm and the approximate algorithm, where at the stage where we go from the vector to the permutation, we only scan the structure preserving permutations, but we assume, because we use the approximate algorithm, we assume that the molecule is too big for the exact um, structure preserving permutation search. So we do not look for all the possible permutations, but we keep track of this sum while building the permutation. And if this sum gets too big, if it passes a threshold, then we cut this branch of the search tree. So this also works pretty well. And let me also mention that that all these algorithms are implemented and can be used on our publicly available website, and also you can download the software and use it. So at the last part of the talk, I would like to describe the application to crystals, but perhaps if you have any questions so far, please feel free to ask.
Indeed, any questions on the case of molecules? Okay, then could I ask to encourage others? So you mentioned that you approximate with continuous similarity measure, Gil, right? May I ask if you have any guarantees on this approximation? So how close is your approximation to the ideal exact value?
Right. No, it is entirely heuristic. In one of our papers, we describe in a practical way how, in which cases, the best algorithm to use. But yes, it's really practical algorithms that you have to try and see for your case. But usually, you can, once you use the algorithm, then you can see for yourself if it worked or not. For example, if you use an approximate algorithm, you get a permutation, so you can see how well it preserves the structure, and you can. What we also produce, which is very useful to the chemists, we also produce the structure pK, which is the nearest symmetric structure. So you can look at this structure and check whether it makes sense on a chemical level. And then I think this also provides some method to see whether the algorithm, the approximation is good enough. But of course, also you can increase the number of initial points and see if it gives you a better approximation.
Okay, thank you. Any more questions on the case of molecules? Okay, then we could go here to crystals and have more questions later.
Okay, of course you could ask later. Yes, so now let us turn to the fascinating world of crystals and crystallography, which is the science of crystals. So, for example, here I took from Wikipedia the image of the salt molecule. So it is just it has two types of atoms, and they are arranged in this very uniform grid. So it is an example of a crystal structure. So a crystal structure is a periodically repeating atomic structure, like in this case. And we have a world of crystals. This is an example of an anorganic crystals, but there are many organic ones as well. And the crystallographers describe the crystal by a small unit called the unit cell, which is just a parallelepiped with some atoms inside, and then a lattice of translation vectors. So you can look at the unit cell as a tile, and then you tile the space with identical tiles to create the infinite structure of the crystal. Of course, in nature, it is not infinite, but it is very, very large. And the crystallographers are always interested in the symmetries of the crystal because they really determine the properties and the family of the crystal. So the symmetry group of a crystal is called a space group. And there is a difference between crystals and the symmetry of crystals because the symmetry of crystal doesn't have to preserve a fixed point. And in fact, they don't. I mean, not all of them, because we always have the translation vectors. So the symmetry groups are always infinite, and they are called space groups. And the possible types of space groups were classified in the 20th century, and there are 230 different space groups. So what kind of operations do we have? So we have all the operations that we had before, like rotation, and so on. But we also have the translations. We have screw rotations, so in which you do a rotation and translation, and you have glide planes where you do a reflection and a translation. And of course, you have the previous one composed with translations. So the question is, how can we find approximate symmetry in crystals? Because again, it is the same situation that the symmetry is not always perfect. So one answer that is an immediate answer that we can just take the methods that we already had for molecules and just apply them to the unit cell. So let us focus for now on the case of inversion. And inversion symmetry is a very important type of symmetry. It has a lot of chemical significance, and actually a very large portion of the crystals only have inversion symmetry. So it is a particular case, but it is a very important one. And let us know that if we have an inversion symmetry of the unit cell, then it will extend to inversion symmetry of the whole crystal structure. But we cannot say it in the other direction, because sometimes we have to look at the shift of the unit cell. So let us look at an example. So here we have on the left, we have a certain unit cell, which is usually provided to us by the crystallographer who analyze the structure using diffraction methods. And this is actually a real world case. So this was the unit cell, but this unit cell does not have an inversion symmetry. But of course, we cannot just think separately of this unit cell, because the crystal, it doesn't know what the unit cell is, because it is many copies of the unit cell. side by side. So we can actually take part of this unit cell and part from the next one, which is just a cyclic shift of our unit cell. So when we do this cyclic shift, then we get a unit cell which has a very good, although not perfect, inversion symmetry. So one basic algorithm that we actually implemented is to look for these shifts of the unit cell and apply the previous algorithms of symmetry search to them. And this way we get a continuous symmetry measure. Of course, we will look for the shift which has the minimum symmetry score. So this is actually our most recent published work on how to use it. And of course, our paper has many examples on the usefulness of this method. Yes, so this is what we write here. By running the point group CSM algorithm on the unit cell and the translate, we can evaluate the inversion symmetry of the crystal. But now let me, to conclude this talk, describe to you our work in progress on how to generalize this to other types of symmetries and higher symmetry groups. So let us look at any type of space group, one of the 230 space groups. And and now, of course, we have infinitely many atoms, but let's just look at the positions of the atoms in the unit cell. Denote the translation lattice by L. So, like in the molecular case, we will look for the nearest symmetric structure, but this time it should be both symmetric under the group and periodic under the translation lattice. So first we need to ask ourselves, how can we measure the distance between two periodic structures which are infinite? So we cannot take an infinite sum of squared distances, but then we can just take representatives modulo the lattice. So the natural space for this is the quotient space. So we take as a mathematical group, we take the Euclidean space and we divide it by the lattice of translations, and then we obtain a torus. So let me expand on that, because this is the fun part. So if we are in dimension 1, then we just have the line, and the lattice is just the integers, or a multiple of the integers. So when we take the quotient step, then we have to identify 0 and 1, and then we just get the circle. If we are in 2 dimensions, then we can take the unit cell as a parallelogram, and then we have modulo the torus. Then we have to identify these 2 edges and these 2 edges. So identify one pair of edges and you get a cylinder, and then identify the second pair of edges and you get this nice donut. And in dimension 3, it is harder to imagine, because this quotient step space cannot be embedded in 3 dimensions, but it still exists mathematically. And we have a distance function on the torus, which is basically when we look at 2 points in space, then you look at the minimum distance between one point and the translated image of the other point. So, for example, if we are in dimension 1, then the distance between point 1 and point 9 is 0.2, because 0.1 is the same as 1.1. And if you lived in the 80s, then you must be familiar with the Pac-Man, where you can go out from one side and come back on the other side. So actually the distance from this point to the point on the other side of the screen is very, very small. And I also noticed, Vitali, that in your recent paper you also use this distance, and of course it is something that has been used.
Okay.
But using this distance, then we can define the distance between two periodic, with respect to the lattice crystal structures, as the sum of squared torus distance between these points when we take representatives modulo the lattice. So the symmetry measure will be the minimum distance between our set of representatives of the atoms and a second set of representative, which will represent a perfectly symmetric crystal. And then we have to define the normalization factor. So let us not get into that right now. But then it's really, we have transformed our problem into the torus, because this, if we take a space group and the group of translations denoted by T, then G mod T is a finite group, which is actually called the point group of the space group. So let us assume for simplicity that it is identical to the translations by the vectors in the translation lattice. Then the elements of this quotient group are the symmetry maps of the torus. And then the perfectly symmetric structures, they correspond to finite sets in the torus, which are invariant under the action of this group. So basically, we can have here the same definition of the CSM, the continuous symmetry measure, when we have replaced the Euclidean distance with the torus distance and a certain normalization factor. So this is the basic idea, but of course we're still working on the fine details because these space groups, they introduce some subtleties and complications, and of course we also have to adapt our algorithms to work in this new regime. So let me conclude. Yes, so we talked about the continuous symmetry measure, and it is a valuable metric of the molecule or of the crystal. So the point group symmetry methods are quite established, and they have been used by many researchers who also used our software. And we can already use them for this group of just the inversion, which is called by crystallographers P and -1, and some very simple other cases by just applying the previous algorithm on the unit cell and the translations. And we're working on general methods for general space groups. So, and we also have this list of publications that we have on the subject. So the last one was really published over the last month, and where we describe this application for inversion symmetry. And sorry about that. And this AI is taking over the world. Okay, I'm sorry. So anyway, there it is. There is our website where you can use these methods. Okay, so thank you very much for your attention.
Thank you, Gil. Let us thank our speaker. Yes, you could keep the slides in the form convenient for you, so that we can ask questions.
Yes, I just wanted to see you because
I
couldn't
don't
see.
worry, we are still here. I'll stop the recording.